But, we're going to record if it's the same thing for all of you, right? Like if you guys have something you need to do that's more important right now, like go study for econ or study for our test or whatever, then, you can go do that. That's okay. I'm not going to be offended. And again, like we record everything, right? Here, let me get my polls up here. I need a new window for this. Let's put that. Ooh, that is not a good place to do that. Ooh, that's really not a good place for that. Okay. Let's send you there. And let's send you there. All right. Better. All right, so this question is actually going to help a lot with your next assignment. I don't know if anyone's looked at it. I know at least one of you have because you've already asked questions on Piazza about it. But yeah, so you probably haven't looked at your next assignment yet. It went up yesterday. This is going to help a lot for that one. All right, so you might be like, oh, why do we care? And this is actually, this is a PDE that ends up being used in economics. So it is actually related. It's not just some sort of math thing. Yeah, I'm trying to remember. I actually forget what the equation is called. Aziz, do you remember? It's it's not Black-Scholes. Yeah, this equation. It's something in economics. I don't remember what it is though.
I honestly thought it was just the utility function.
Maybe it is.
I think it's just the utility function. It's just a version of the utility function. Because there's a couple of them that we end up doing, and I'm trying. I had a specific. It's called the Cobb-Douglas, I think.
Yeah, that sounds right.
The Cobb-Douglas one.
Yeah, something like that.
I haven't done utility curves in just a minute, and I like a period of time now, so this is kind of off the top of my head, but that sounds about right there.
Yeah, that does sound right. That sounds. I'd have to check our notes on this problem, but that sounds right. Is it going to be like the term test, or is it going to be completely different? It's going to be very similar. I think really sort of structurally the only difference is it's going to be longer, Jacob. Right? It'll be like 6 questions or 8 questions or something like that. But otherwise, it'll be the same sort of format, same sort of difficulty level, that sort of thing. Actually, in my experience, and I've said this before as well, we tend to make the final easier, but students just struggle with it more because what do you remember from linear algebra, right? Oh, Jacob, that's a hot take. I'm sure some people in this class really agree with you, and some people, some people not really agree with you. Probability is a love-hate unit. Like some people really like that unit, some people really hate that unit. Yeah, see, and linear algebra is the same way, and finance is the same way. Nobody cares about calculus in the sense, like differential calculus isn't. People don't have strong opinions about it, but people have strong opinions about that first semester material. Yeah, that's true, James. That's totally a valid sort of thing, right? Where it's easy to do something that seems correct, but is actually incorrect, right? So it kind of crushes your confidence. And that is sort of a thing that you kind of can't get around, unfortunately. It is like that. Well, that's interesting, Terrace, because again, some people like really hate some of the material in first term, right? Usually there's probably a subject, like a topic in there that students enjoy, but again, finance hit and miss. Some students really like the finance section, some students really hate it. And probability and linear algebra is also the same way. It's really weird. And I don't know if there's anyone who liked all of those sections, but well, that's not bad. There's nothing wrong with that. Yeah, and that's something we were really worried about, right? Was like how much math did our students really learn the last year or two? just with so many interruptions, so much COVID stuff, right? And I'm sure it really drastically varied from school to school, from class to class. So it's something that we're worried about. And not only that, it's going to perpetuate for many years, right? Like if you didn't feel super comfortable with your material coming into first year, there is a sense in which that's going to continue to propagate into second, third, and fourth year, right? So hopefully not too much. First year, I find, tends to be a great equalizer. People sort of, from all sorts of different backgrounds, some very strong, some very weak. But first year is an opportunity for everyone to sort of normalize and get roughly on the same playing field. So hopefully we'll see some of that. But huge concern for us coming into this year, where our students would be just in terms of their high school material, because, right, we had no idea. Some students probably did okay, and then some students didn't learn anything the last 2 years. So. Okay, well, that's interesting. Yeah, that's cool. Yeah, some students are like, probably think this class is quite difficult, or maybe not difficult, but like relaxed is not, I'm not certain that's the word I've heard used too much for this class, but I mean, that's awesome. I'm certainly not upset with that. All right, let's do another 30 seconds. I'm going to close this up. We'll take a look at it. That's nice though. Yeah, the class is getting this. This is pretty awesome. Maybe though, does anyone like had seen the answer in econ or something and maybe knew the answer that way? Okay, so like if you had to guess, you maybe had an idea or something, and then hopefully some math backed that up. But all right, let's take a look at this. Let's end that poll. Let's share that poll. Okay, class sort of leaning towards B. That's phenomenal. B is absolutely the correct answer. And let's take a look at why. So again, this is actually going to be super related to what you do in your next assignment. So it's kind of nice to have an idea of what we mean by satisfy a differential equation, right? So maybe let me just rewrite the differential equation. We have L die P die L plus K die P die K must equal alpha plus beta times P. Okay, so what you're going to do is you basically want to compute both sides of this equation and then determine if they're equal, right? So let's just go through the options until we get one that works. Our first option is P is equal to 1 over LK, right? And if I differentiate this thing, so let's compute the left-hand side first because the right-hand side is kind of easy. So the left-hand side has all the derivatives. Let's compute that. So the left-hand side is, okay, so we're going to get L, and now we need to differentiate this function with respect to L. So that's going to give me negative 1 over L squared times K plus K times negative 1 over L K squared, right? And we can cancel some L's out. So what is that going to give me? Negative L over K minus 1 over LK. So that's negative 2 over LK like that. Okay, is everyone okay with those things in the square brackets, like how I computed them? If not, let me know. And the right-hand side is just alpha plus beta. Well, there's no alphas or betas, so this is already probably not a good sign. P, so that's alpha plus beta over LK. And if I look at these two things, generally those aren't going to be equal, right? Okay, so I got a direct message saying, hey, I didn't see how those were computed. So let me do one because they're the exact same, right? In terms of L and K, totally symmetric. So if once you compute one of them, the other one is the exact same. So if I'm computing the derivative of 1 over LK with respect to L, so remember K is just a constant here, right? In fact, we can take it out. We don't even care about it. So we just like pull that out like that. Right, die L, 1 over L. And then we know how to differentiate like 1 over X, right? It's negative 1 over X squared. So this is the same thing. It's just instead of X's, we have L's. So we get 1 over k times negative 1 over L squared, like that. And then you just put them back together, right? KL squared, like that. And then the k derivative exactly the same, right? It's just L is the constant there, but you still get the derivative of 1 over k with respect to k. So you get that negative 1 over k squared, exact same thing. Okay, so does that make sense? So it's not this one, right? Unless we have very special values of alpha and beta, like say both of them are -1 or something, is generally this isn't going to work. And we're looking for something that works for all alpha and beta, right? So it's not A. If we go to B, now B is the correct answer, so this should work out. I probably won't do C or D, but you can do them for practice if you want. It is good practice. But I want you to see that this is going to give us the right answer. So in this case, here, maybe let me compute these things separately. So here, we've got P is L to the alpha, K to the beta. That's a good sign. At least we actually have alphas and betas here, right? So if we compute di P, di L, again, K is just a constant. It's just going to come along for the ride. So we're going to get alpha L to the alpha -1, K to the beta, right? I use my power rule here. And then this thing is just a constant, so nothing happens to it. And then if I differentiate this with respect to K, again, these two things are totally symmetric in L and K, so you're going to get the same sort of thing, just with the appropriate changes for K instead, right? Beta, here, maybe let me write it on this side, beta -1, L to the alpha, like that, okay? So we get power rule, and L to the alpha is a constant. So L di P di L plus K di P di K. Let's go and let's plug those things in. So we're going to get L, alpha L -1, K to the beta, plus K, beta L to the alpha, K to the beta -1. So this has the effect of, L times L to the alpha -1 is going to add that 1 back into the exponent. So I'm going to alpha L to the alpha, K to the beta, plus beta L to the alpha, K to the beta. And if you factor out that L to the alpha, K to the beta term, alpha plus beta, L to the alpha, K to the beta, that is P, right? So we don't actually have to compute the right-hand side separately this time. We do actually just, everything sort of falls out and we get what we want, right? So that's how we know this is the right answer. And in theory, if we didn't get the right answer here, we'd go to option C and we do the same sort of thing and we do these computations. We would get logarithms and stuff like that. Same thing with D, right? So you just have to compute them. If you want to check that something satisfies an equation, what do? You plug it into that equation and then you verify that the two sides are in fact equal. Again, your next assignment's going to have something like that as well, where you're going to have to plug it in and check that both sides are equal. And that's just how you do that. Okay. So are there any questions about that? And again, practice C and D for more if you want. Phenomenal question. So I got a direct message that says, what would we do if it's not multiple choice? The answer is you go home and you cry. Solving partial differential equations is an entire course, and it's typically a third-year course.
I was going to say, that's really true.
It's real hard. So yeah, just start crying into your paper and hope that the tears evoke some sort of sense of sympathy, right? Because yeah, it's actually really, really hard. The thing that we're going to have you do in the homework, which is the wave equation, which is really important, right? Because lots of stuff in life is waves. Like I'm communicating to you with waves right now. These signals that are going through the fiber optic cables of our internet providers are all done in terms of waves. So waves are super important. Those things are infinite sums as a general rule. In order to be able to solve them, generally you require infinite series and Fourier stuff, and it's very messy. So yeah, it's tough. So these sorts of questions, 100% we give you the solution and we say, check which of them are the solutions. Yeah, I probably wouldn't give you something like that on an exam. I could give you something like this though, right? Where I say, check that this is an answer or determine which of these is an answer, is a solution. You could totally do that. There's no way I'm going to ask you to solve a PDE. They're way too hard. Right? That's how the people who make the big bucks, that's what they get paid for, right? It's to solve PDEs.
I was
So
gonna say if they know you after the test and there's a lot of cheating cases, you might add one in the final exam.
that's right. Yeah, just to see what happens when people start pulling out solutions to PDEs on the final exam. That's a big sign that something happened. All right, here I'm going to skip this one. Let's just do this one really quick. So this is good, sort of like final exam practice. I know you guys probably aren't. Oops, sorry, not share. I know you guys probably aren't studying for it yet, but this is something from your final exam. This is actually a great final exam question. Sort of is a question of, do you understand both the probability section and multivariate calculus?
If I want to add something, these are like Tyler's bread and butter type questions for the final exam. Like not just necessarily this question, but more like mixing topics together, right? Because it shows whether you understand the topics, actually understand them, or were you just learning a few formulas and hoping one of them worked, right? In
And
the
you guys
final
have
exam,
seen,
you can't do that.
yeah, you guys have seen that, like I've asked you to solve linear systems, right? Outside of the linear algebra thing. So yeah, totally, you guys could be asked to do some stuff like that, right?
The thing is, I see sometimes the test, because the information, like you're testing them on a limited portion of stuff, they memorize like 5 to 10 formulas and they try to like brute force the 5 to 10 formulas until one of them works. But in a final exam, when you have the whole course ahead of you, you can brute force test like 1,000 formulas until one of them works, right? So this is where like the actual understanding kind of rises up, and you can see whether someone actually understood the topic or it was just kind of floating through it.
Yeah, and it's nice to merge things too, right? To be like, these topics don't just exist on their own. In reality, you combine them. So one of the things we're actually hiding from you all is there's actually a lot of linear algebra that happens in this section. This entire section is actually all linear algebra. We've kind of like swept it under the rug so you can't see it. But you guys remember doing eigenvalues and eigenvectors? That's actually a huge part of next week. And again, we've like mostly hidden it. But eigenvalues and eigenvectors, hugely important to next week. Also, they show up all the time in the probability section, eigenvalues and eigenvectors. So those things show up everywhere. We didn't do those applications where they would appear, but they are there. They do exist. And in fact, they're in the notes. So if you go and you check it at the end of the probability section, you can check in on something called Markov chains, which are super important modeling tools. And yeah, you'll see eigenvalues and eigenvectors show up there too. Oh, this is nice. The class didn't, the vote started off a little shaky, but class is coming together. Interesting. All right, 30 seconds. It is. Yep, Connie, it is. That's okay, as long as you got to the right answer eventually, right? That's all that matters. It's not worth marks, so who cares if you get it wrong, right? As long as you eventually get to the right answer, that's all that matters. Okay, so let's take a look. Class is leaning towards A. We don't quite have a majority in A, but A is the correct answer. So again, there's sort of like a counting thing that's going on here. And I don't even think I need to pull up the my OneNote or whatever. We can sort of do it from here. So first of all, if the question were asking how many sixth order partial derivatives are there total, what would the answer be? So maybe question, how many sixth order derivatives are there? Total. Okay. B, yes, yeah, exactly. The correct answer is B, which is 4 to the power of 6, right? Why? Because you've got 6 slots, right? And inside of each of those slots, you can put one of 4 variables, X, Y, Z, or W. So you've got 4 options here, 4 options here, 4, 4, 4, 4. And then our basic counting principle says that we multiply all those together and we get 4 to the power of 6, right? And like, that's a crazy number, right? Like, think about how big that number is. That number is 64 squared, whatever the heck that is. It's on the order of 3,600 or so, right? So when we were dealing with functions of a single variable, you could, we didn't very often ask you to find a 6th derivative, but there was only one of them. If I give you a function of 4 variables and I say find all the 6th derivatives, ostensibly, there are about 3,600 of them, right? So gross, that number multiplies really quickly. But in this problem, we're not asking you to find all of those, right? We're saying how many of them specifically are of this form. And one of the things that hopefully you learned is that in Clarue's theorem, or in this case, the generalization of Clarue's theorem, is that the order of these actually doesn't matter, okay? If you're taking an x, x, y, y, z, w derivative, you can actually take those derivatives in any order that you want. So you could have done x, y, x, z, w, y, or something like that, right? It's 4 because we have 4, because you have 4 variables. Yeah, so you have x, y, z, or w that you could put here, or x, y, z, w, right? So you could do like x, 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 x. You could do x, 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 y, and so on and so forth, right? So you get a lot of options. So yeah, so it's 4 because of those 4 variables, and it's 6 because of the number of derivatives. So Clarue says you can compute these derivatives. Okay, sure. So you can compute these derivatives in whatever order you want. So this is the same, remember when we were doing probability and counting, as saying how many words can you make by rearranging these letters, right? And we know what the answer is. It's 6 factorial divided by the number of repetitions. 2 factorial, 2 factorial. And then if you want, you can include, 1 factorial here, but those numbers are just 1. Here, maybe let me put them in. Like so, right? So from probability and counting, the number of ways of, rearranging these words or these letters is 6 factorial, but there's repetition. So I have to be able to account for that. And that's why we get A. Okay. Yep, it totally happens. But luckily, you can see that this, the problems in terms of counting derivatives don't get too much harder than this, right? So we've talked about how to compute the total number of derivatives, and we've talked about how to compute the derivatives of a particular type. And they're all sort of these repeated letter problems. So they all basically have the same format, right? I just used the thing that n variables to the power of 6, since there are 6 times that we do the derivative. Yeah, Rafid, that's basically the same reasoning. Yeah, that's basically the same thing. I think that's okay. Yeah. Okay. Any questions about this? So this is an interesting question, which is like a lot of people aren't going to write this test because they did so well in the first ones. If a lot of people don't write this test, will it be curved? So we don't necessarily do curves on the basis of how everyone performed. We generally do curves on the basis of whether we thought it was fair. Now, if a ton of the class does poorly, that's a sign, right? That's a sign that maybe it was too hard. And then we go back and we take a second look at it. But generally, even if the class does poorly, but we think the test was fair, we wouldn't do a curve or something. This did actually happen a couple of years ago, and the class has never forgiven me for it. But we gave a test. We thought the test was fair. It was in the finance section. And actually the finance test you all wrote was way harder than what they wrote. But so they wrote the finance test. They did very poorly. We went back, we looked at it in great detail. And we were like, no, we covered a question like every single one of these things. This matches with what we did in the assignments. So we're not going to curve. And the class did quite poorly. And they're still, like I said, they're still quite angry with me about it to this day. You can go and you can talk to like 3rd and 4th year students who are just, ticked off about that still. But I mean, I don't think I've done it this, have I? I don't think I've done an adjustment this year, have I? Jackie, I just don't submit. And when I go through, like, you'll get a 0 on this test, but I'll just drop your lowest score, right? So you get a 0, but then I drop your lowest one. So you don't have to do anything. It's fine. Yeah, I haven't done an adjustment, which is maybe a good sign that we've done some good stuff. Yeah, sometimes I can't, like, again, we might do an adjustment, we might not. We won't know until after the test, right? Yeah. Well, I also, like I promised, I said I would always tell you if we were going to make an adjustment. I would always tell you at the time, right? So you always knew exactly what your grade was. So that's a thing too. Ooh, okay, I like this question. This is not too bad. But wait, wasn't term test 3? What was term test 3? What was it on? Was that the probability one, or was that linear algebra? Maybe it was linear algebra. No, it was probability. Jacob, weren't you saying you love the probability section and now you're saying you hate term test 3? Okay. Well, listen, everyone, there are ups and downs, right, in your tests. And that's life, right? I don't want you to worry too much about having a bad test here or there. It's okay. Everybody has bad tests. I promise you. You go talk to any professor, and if they tell you, yeah, I never did badly in a test, then you call them a liar. Maybe not to their face if they're an active professor, but everybody's had bad tests, right? You go through your life, you go through your university career, you're literally going to write hundreds of tests, right? So a couple of them at least are bound to be bad. Some of them maybe more than others. That's life, right? I've written some terrible tests in my life, no doubt about it. Oh, I didn't restart the polls. There we go. So when you compute the Hessian, Connie, your answer should, as a general rule, depend on X and Y, right? And so when you evaluated it at a point, you're actually plugging in numbers for those X's and Y's, and the thing that you get out should just be a matrix, right? So that's the sort of thing there. When did I realize I was passionate about math? Oh, I mean, in reality, I was probably like 4 or something. My mother loves to tell stories about how she used to buy those books, that had just like tables and tables and tables of addition problems and multiplication. And I would apparently just tear through those at a young age. And, she just ran out of them too quickly. And yeah, I guess I've just always enjoyed doing that stuff. So always, but I wasn't always committed to being a mathematician. Like there were some times where I was considering med school. There were some times where I was considering, doing like computer science. So it hasn't always been math, but it's always been, sort of academically related. Yeah. Yeah, sure. Yeah. I personally would love to, so as a professor, I actually get free tuition, right? Rafida, I'm actually the video on Hessian. I got confused. So Rafid, can you actually send me maybe a screenshot of that, or a link to the time there so I can take a look at that? Yeah. No, I mean, just like, so as a professor, I actually get free tuition. And I always think, like, if I were to retire and wanted to like go back to school, what would I do? And the answer is a lot of things, because I legitimately think like history is a super cool subject. It's not something I'd necessarily like to try and make a career out of, but I think history is pretty awesome. or engineering. I think, being able to apply the mathematics that I know to engineering problems would be super cool. So I always, think about going back and doing some of these things. And yeah, it'd be interesting. But then I'm just like, maybe I should just study those on my own, right? I don't need to go to school for that. But I think, and some of you probably get this too, sometimes it really helps to have that structure of a classroom to help like keep you on track. Because when you're like, I'm pretty self-motivated, but still sometimes I'd rather just hang around. Oh, you're right. There actually should be 3 zeros, Terrace. Good catch. There should be 3 zeros. It turns out, of course, it doesn't actually matter once you do the problem. Yes. So Rafid, there are 2x2 matrices. That's because I'm computing a determinant here, right? And so when you compute the determinant, remember you take the submatrices, like you expand over a row or a column, and then you delete that row and column, and then take the determinant of the submatrix. Do you remember that? So I am 100% there adding, not adding like, yeah. So it might just be a matter of going back and checking on, well, here, maybe we can find the determinant video and that will, linear algebra, where are you? Determinants, and let's, all right, that's kind of a boring example. Do I do a 3x3 anywhere? I don't seem to have a, wait, is this, oh, this is the inverse. I'm totally looking at the wrong video. Let's see. Yeah, okay, here. So let's share this. All right, so here is the determinant video. And here I do a 3x3, and you'll be able to see like that it breaks down into a bunch of 2x2s when we do it. So just give that one another watch, and hopefully it'll make more sense. All right, everyone, I'm actually going to lock this down in 30 seconds. So let's get our answers in. Okay. All right, so class is leaning towards C apparently, which isn't a bad guess, maybe. It's kind of a weird guess, but yeah, we'll stick with it. The correct answer is D. And let's see why. So one of the things we could actually do is, do I want to, let's choose one number. Okay, so everyone choose, like, do you want to compute the x derivative, the xy derivative? No, okay, not that number. Do you want to choose like the xy derivative, the xz? Okay, sure, yeah, let's do the main diagonals. So yeah, you're right. I think that is maybe the easiest. So let's do the main diagonals, because we don't, for this, it's a multiple choice question. We don't actually have to compute everything, right? All we have to do is compute, entries until we find one that doesn't work, that doesn't match what we're doing. So let's compute the main diagonals for each of these problems. So the first one, A, we have f of x, y, z is 2x minus, oops, I put that equal sign, 2x minus y minus z. So if we compute the x derivative, what do we get? Yeah, exactly. Yeah, like it's a sort of thing that's like once you see how to kind of read them off from the original function, it goes really, really quick. Exactly, Connie, exactly. 0, what's the y derivative? And I mean, we could stop here, right? Because the x derivative is the 1 element of the matrix, which we know has to be 2. And once we get 0, we're done. Yeah, 0 as well. And the z derivative. Zero, right? Okay, so that's not all the elements of this matrix, but it should be the main diagonal, right? The main diagonal is x, y, z, z. We got zeros here. This doesn't agree with our matrix. Let's throw that out, right? And again, we even could have stopped after the x derivative. Why is it? Why is which one 0? Or like, just how do I do one of these? So the x derivative is 2, and so this thing is a constant. So if I differentiate it again, I get 0, right? Same thing. The y derivative is -1, and if I differentiate it again, I get 0. And then the z derivative is -1, so if I differentiate it again, I get 0, right? All right, so hopefully that makes sense. So the next one is x squared z to the -6 plus xz minus e to the -3xz plus 4xy. Okay, let's compute the x derivative. So what do we get? We get 2xz to the -6 plus z plus 3z e to the -3xz plus 4y. Does that look right? I'm not sure I see it. Okay, does that look right? Okay, unless somebody yells at me, I'm going to assume. Yeah, Kubernetes. Yeah, it's just the derivative, right? With respect to whatever variable you say. So if I do now another x derivative, hopefully this isn't terrible. So I'm going to get 2z to the -6. That's 0. So this is going to be minus 9z squared e to the -3xy. And then that part is 0. So I get this. And now if I plug in 0, 0, 0, what do I get? Well, I get something that isn't even defined here. And then I get 0 here. So this is just undefined. Right? So it's not B. And so on and so forth, right? Like you continue to do this process until eventually you get to D, which is x squared minus 3z squared plus xy minus 3xz plus 4yz. And again, you can go through, you can actually compute all the derivatives of these things. You'll get the x derivative is 2x plus y minus 3z. So the x derivative is just 2, right? And that's what we need because that's the 1 element of your matrix. Or while we're here, you could do the dyx derivative. So that's the derivative of this with respect to what y. So that's going to be 1. Or the dzx f derivative, which is the derivative of the circled thing with respect to z, and that's -3, right? And we see like that is exactly the first row and column of our matrix. So yeah, this is a really good sign, right? And if you go and if you compute the other things, it'll work out there as well. Undefined and B, sure. So just like 2z to the -6 is 2 over z to the 6, right? So if we're plugging in z equals 0, we can't divide by 0. So that's just us saying like, oh yeah, that thing doesn't make sense. Okay, and so we see here actually, based off of this thing, because this is, basically a degree 2 polynomial. Oh, this is 4yz. But this is a degree 2 polynomial. So it turns out when you differentiate this thing, you're actually going to get constants. Most things, when you differentiate them and you compute their second derivatives, will still depend on x and y and z. But in this case, because everything is a quadratic polynomial, you end up just getting constants at the end. So actually the numbers that you plug in don't end up mattering at all. Now, sort of the interesting question to this, which I think is a good exercise for you to do, is what happens if we reverse the problem? So I gave this as a term test question one year, everyone. So it's probably good practice if you wanted to try it, which is to go backwards. So which is to say, if I gave you this, right, can you find a function, right, like one of these? So write down sort of a matrix at random. Okay, it's got to be a symmetric matrix though, right? It's got to be, it's got to be equal to its transpose. So write one of those things down and see if you can come up with a function that gives you that as the Hessian. And big hint here, your best bet is going to be to choose a polynomial, right? Don't do anything more complicated than you have to do and throw in exponentials or anything like that. Figure out, given this thing, how do you write this as what function did that come from? What quadratic function did that come from? Okay, so that I think is going to be sort of like a good idea to do there. Let's get rid of this stuff. All right, let me see if I can't get one more in. What question do I want to do while we're here? Yeah, let's do this one. Just a quick and dirty chain rule question. And hopefully you see, you probably look at those options and you're like, oh, I'm blind because, oh, gross. But it is short, the sad thing about notation for multivariate calculus, that the notation is quite inadequate.
While you guys are working on this question, I'm just kind of curious, how's everyone's prep for the test in a few hours? Nervous, depressing, great. I was hoping not to hear, I'm not doing it. Okay. I got a lot of private messages as well. Some people said I haven't checked the syllabus yet. That's not a good sign. Some people saying I'm not doing it because they did did really well on the 500 test. Wow, I actually have at least 4 people that message me probably said they're not doing it. Fair enough. I guess you guys did really well in your other 5 tests. I mean, thing is with a lot of this stuff, especially when we go to the multivariable calculus portion, it's a lot they have a lot of a big implications that you probably wouldn't unless you continue in math, you'll never understand the true depth of how some of these things work. So the only thing you can do I think for this chapter, the best thing you can do is a lot of practice. Just because there's some things that are in this chapter that I'm pretty sure Tyler also highlighted, that it's just you won't understand the full grasp of how they're done until you take further level math courses, right? But we teach you kind of the basic of the basics more than anything else. So just practice and practice and practice for this section more than anything else. Tyler, I asked how prepared they were for the test, and I got at least 4 people private messaging me saying they're not doing it. They're going to rely on the marks of the first 5 tests.
Okay, yeah, I mean, that's your freedom, right? Everyone's prerogative is to do that.
No, I just want to do. I think the future. they're being, I don't know why they're being too nice to me. I think they know I'm still grading their material, so they think that that's why they're being too nice to me right
That's
now.
right. That's exactly it.
I mean, I've also been doing this for a while, unfortunately. I taught this course 7 times. This is my 7th or 8th time teaching this course. So like,
Yeah.
so I think I'm a veteran strictly. I'm decent at this strictly by repetition more than anything else. When you see the same type of questions like 5 years in a row, you're bound to kind of get good at them.
Mm-hmm. Yeah, but Brandon, like it can't drop lower, right? Like if this is your worst test, then it gets dropped.
I agree. Like it's one
Like
of
there's
these
no
where,
reason
like,
not to write.
I agree. Actually, that's a good point. Like I would write this regardless because like even if you end up with a 0 on the dot, this will be your worst one. And if you didn't write 3, you're gonna end up with a 0 anyways.
Yeah. So basically, if you don't write, you just get a 0 on the test, but it gets dropped, right? But if you do write and you pull out a better mark than one of your previous tests, then that one gets dropped. So there's really no consequence to writing. But that being said, like if there's other stuff you have to do, like if you have to worry about econ, then go do that, right? Like don't worry about it. Yeah, Brandon, that's true, I suppose. But you just, again, especially if you have to study for other tests, it might not be worthwhile. All right, see you, Aziz. All right, let's lock this down 15 seconds and then we'll take this up. And I think I could probably even do this on this screen. Yeah. Okay, so let's take a look at this. All right, class sort of is leaning towards B, but in this case, C is actually the correct answer. Okay, so we have to be really careful about what we're depending on, right? So remember, when we talk about the chain rule, we have to make sure that we create that dependency tree. So that dependency tree is going to be absolutely critical for us figuring out how to take derivatives. So the dependency tree here, let's take a look at it. So here, W depends on X and Y. All right, so let's draw that. W depends on X and Y like that. Okay, and now, okay, X depends on S and Y. So let's draw that out. So X depends on S and depends on Y. And then Y depends on S and T. So let's draw that. S and T, S and T like that. Right? And so now we're asked to find the derivative of W with respect to S. Right? So we want W, S. So what we want to do, how can I change my color? Oh, here we go. So what we want to do is we want to find all the paths from S to W, right? Okay, that's how we're going to figure out the chain rule. So we're going to find all the paths from S to W. So here's one, right? So if I take this path, I'm going to get W, X, X, S. Right? So you just follow up the path where you differentiate the top variable with respect to the variable just beneath it. Okay, let's change our color. Here is another path right here from S to W, right? So I'm going to get plus W, X by Y by S. And then there's only one other path. What color can I use? This one? The other path, oop, stupid thing, go away. The other path is this one. So that would give me W by Y by S. Okay, and the culmination of those three things is exactly that result right there. Okay, does that make sense? So you figure out the tree and you trace from the bottom of the tree to the top of the tree, and then you can use that in order to write stuff down. So your answer in this case is C. Now, a lot of students said B, and B would be what would happen if this was like, what? So if this were a T here, right? But we have to be careful about that because it's not that X depends on S and T, X depends on S and Y, right? So we have to be careful. Okay, Jacob, I assume that's about this. So can you elaborate what's bugging you? The T, or maybe here, let me get rid of that thing. I don't want this here. Yeah, ignore that T. That's not what we want. Yeah, or let me maybe say this. Yeah, okay. I guess B is correct, except it doesn't account for the fact that X has another dependency on S, right? X depends on S in two ways. Let me see if I can do this. So X depends on S in this tree and on this tree, right? Yeah, there's two dependencies. So we expect there to sort of be like, here's one of those dependencies, right? It can directly depend on S, but it can also depend on S through its Y dependency. And so it has to, that's why B can't be the correct answer, because we're missing one of the dependencies of X through S, right? Right, but that's just it. Like, that's why we set up this tree, right? Because we have to be careful about that. Right? Like X depends directly on S, but because Y depends on S, X also depends on S through Y. And so we have to take account for that when we're taking an S derivative, right? If your variable changes with respect to S, and you're trying to figure out how, right, what is di S? It's the instantaneous rate of change of W with respect to S. So you need to figure out every single way that your variable W depends on S. And that's why we build this dependency tree, to see all the ways that W can depend on S, and then use that in order to figure out what the derivatives are. Yes, yeah. So generally, Lee, that's how I would do this. Build your tree, find out all the possible S's in the tree, and then just follow those S's back up into W. And it's always a tree. So there's always a unique path from your S at the bottom to your W at the top, and follow that all the way through. And that's how you figure out what your chain rule is. I mean, you could go down if you want. It's just a matter of perspective, right? I personally think it's easier to start from the S's at the bottom and go up to the W at the top. But if you can look ahead and start at the W and say, okay, how do I go down this tree to get to the S's? Then that's totally fine, right? The point is just try and find all your paths from S to W or from W to S. And there will always only be, for each unique S, there will only be one path to it, right? Because nothing like here, let me see if I can do something weird. Nothing like this can happen. Like, you can't have a cross path, right? Like that can't happen, right? So it doesn't matter if you start from the bottom or the top. You can always just, there's one and only one path from every W to every S. So that doesn't matter if you draw it this way. Okay, is everyone good? Otherwise, we'll go into office hours. Give me a shout out if you need a little bit more of this, because we write the differential sequence the way. Yeah. Okay. All right, right on. So here, let me get rid of stuff. I've got a couple questions already people are asking about. So let's see. I just got to open my copy of the notes, because of course that's where most of it is. So 829, I feel like we did 829. Did we not? We did do 829. Let me maybe pull it up as a video so whoever asked that can see it. Did we do 26 as well? I don't remember. Somebody asked for 826. Did we do 26? I guess we did 24 the other day, so we can do 26. It's similar. 9495. But let me get the video for 29 first. Anyone remember what that was? That Tuesday, last Tuesday? Jacob, you could. That's the sort of thing, though, that you should have just thrown your partner under the bus and said they didn't respond. You know what I mean? Because like they shouldn't be doing that. That's why there are those internal deadlines. Yeah, yeah. I mean, you can ask and see what happens. Q3 of last week's assignment. Sure, I'll add that to my list. Sure. Okay, so let me find this video first. That way I can kind of maybe just send that person the video and they can check it out. Where the heck is it? So that's 28. All right, here. So I was asked for 829. I did 829 last week in office hours. So there's the link to it. Lee, you should tell me then if that's true, because we have totally prosecuted academic offenses for that. So you definitely should tell me if you feel like your partner is doing that. Okay, so 826 then is next. Here, let me get this stuff off the screen. So 8-26, I guess for 8-26, I gotta pull up I need the graph of it, so just let me do that. $133 notes. Oh, nice. It's practically open to this section. Okay, so here's 8-26, which I was asked to do. And let's maybe make that a little bit bigger so we can see what the graph looks like. Okay, so, and I think, we did something like this on Tuesday as well, just for a slightly different graph. So let's look at part A. We want to determine the values for which A of X is greater than 0. And A is the difference between F and G, right? So that's important, right? Pay attention to this. This is the definition of A of X here. So we want to determine where A is greater than 0. So looking at the graph, just by inspection of the graph, where is A positive? So sort of the first question I think we should ask is it positive here? Like, is this area positive under A? From 0 to 1/2? Right, no, right? It's negative because F is the smaller function on this interval. Arslan, can you be more specific about what part of that is bugging you? I mean, variable names don't matter, right? So we could have called this like F of S, ds, and it would have been the same, right? Like that T there is just a dummy variable, but in particular, we can't use X because we need X to be that thing right there so that this is a function of X, right? So these variables, this variable can't be this variable because the variable inside the integral is a dummy variable. Yeah. Okay. So this area is negative. Okay, so the area, oops. So A of 0.5 is negative. Now, because we're cumulatively adding stuff up, all right, so this area here is positive, but up until now, we already have a negative area. So that's just going to cancel out this area, right? So that tells us A of 1 is equal to 0. So everywhere G of X is greater than F of X, does that mean A of X is negative? Well, we have to be careful about that. So if G is bigger than F, then when we integrate there, because we're trying to find the area between these graphs, we are picking up negative area. But remember, the sum is cumulative, right? So we have to worry, like if I'm negative 100 and then I add 5 more area, I'm still negative. Do you know what I mean? Right? So here, this is what I'm talking about. A of 0.5, not only is it negative, but it's actually, we can figure out exactly what it's equal to. It's equal to negative 0.5, right? So even though now this area here, I don't want white, this area here is positive, it only is a positive 0.5. So it actually isn't enough to make a positive. It's only enough to get it back to 0. Sure. Yeah, I can try and post that tonight. So does that make sense, Christian? Right? Like it doesn't, it's positive area, but if you're already negative, it might not be enough to get you back to positive. So we're 0 at 1, right? We're kind of like back to 0 at this point. Okay, this stuff here, maybe let me color stuff. So like this area here is positive, right? All this area is positive. And this area here is negative. And then this is negative. Right? And then this is positive. Okay, so after 1, after this point, our area is positive again. And what does that look like? It looks like it's going to be positive until about 3. And then the area I pick up looks like it's going to tell me that A of 3 is equal to 2. Do you see that it's equal to 2? Is everyone okay with that? Because I'm just counting the squares, right? So when I count the squares, I've got 1 square here, I've got a half a square here, I've got half a square here. And so in total, I've got 2 squares. And then A of 4 looks like I get rid of a square, or half a square, so I would get 1.5, right? And then here I get rid of another half a square, so A of 5 is equal to is just equal to 1. And then I add another half square, so A of 6 is equal to 1.5. So does that make sense, everyone? You just kind of like go through and you keep track of your area as you move. And we're probably only going to ask you areas from nice numbers, right? Like A of 1, A of 2. We're probably not going to ask you like A of 2.5 because that's a little bit messy. But so you walk through and this is how you'll do it. Okay, so basically what do we get? We get A of X. So A of X is greater than 0 if X is in 1 to 6, right? Or alternatively, you just say X is bigger than 1. So it's only sort of negative at the beginning. Yeah, exactly. At 1, it's equal to 0, right? Because these two areas right here, these cancel each other out. Right? Because they're both the same size, but one's positive and one's negative. So that's why they cancel. So as we move right, we accumulate. Yeah, exactly. You accumulate area, but you can accumulate negative area as well, right? So the green area is positive area, the red area is negative area. So you can have some cancellation like that. But yeah, that's exactly what this means, right? Like this thing means find the area between 0 and X. So that's why you're accumulating that area. Okay, so part B now asks for what values is A of X increasing / decreasing. Okay, so by FTC, A prime of X is just F of X minus G of X, right? So we want to know, so it's increasing if this is greater than 0. So A is increasing if it's greater than 0. And decreasing if A prime of X is less than 0. So now, right, basically, if you look at the graph, it's going to be increasing on the green portions and decreasing on the red portions, right? So it's going to be increasing whenever, here, let me zoom out a bit. It's going to be increasing wherever F f minus g is greater than 0, i.e. wherever f is bigger than g. And it's going to be decreasing wherever f minus g is less than 0, i.e. whenever f is less than g. And that makes sense, right? Remember, we're accumulating area. When am I increasing? Where I'm accumulating positive area, right? Where am I decreasing? Where I'm accumulating negative area. Does that make sense? So you don't have to shade things in for this question if you want. You can just look at where f is bigger than g. But what I want to do is not just like an algebraic sort of understanding, but like, let's look at the function a, right? It is the area function. Where is that area increasing? Where I'm adding area, the green stuff. Where is it decreasing? When I'm subtracting area, the red stuff. Okay. So that means increasing on, let's see, what is that? That's 1/2 to 3 union 5, 6, right? And decreasing on everything else. So decreasing on 0 to 1/2 union 3, 5. I guess I should use open intervals. We wouldn't deduct marks for that. You know, are you increasing when your area is 0? Who knows? Who cares? Okay. And now the function part C is to find the absolute max and min. So our job here is to now find the critical points, right? So the critical points occur when a prime of x, which we already said is f of x minus g of x, when that's equal to 0, i.e. when f equals g. Right? So whenever these two functions touch, we've got a critical point. So our critical points are here, here, and here. And then we also need to check our endpoints. Now, in this picture, we've computed pretty much what all of these things are, right? So we know a of 0 is 0. So that's the left endpoint. A of 1/2 is negative 1/2. A of 3 is 2. A of 5 is 1, and then A of 6 is 1.5. All right, what's the biggest? That's the max. And what's the min? That's the min right there. Jacob, I'd love to. And it was a good try, but yeah, but again, you know, we'd have to find a question. And do you have some tips about how we know if to integrate along the x? Oh, this is a great question. Yeah, here, I can hit this quick. So the question is, you know, how do I know whether I should integrate along the x-axis or the y-axis? There are some instances where it's obvious and some instances where it's not. And the answer is, yeah, you kind of have to play it by ear. What I'd say is kind of like look at the function itself, right? So I always graph the function, and everyone, remember, you guys are allowed to use Desmos, okay? Like, or whatever graphing software you want. So if you have a little bit of trouble visualizing what something looks like, go plug it in, okay? By all means, I 100% support that. So for me, my sort of thing is I'm worried about whether the thing I'm integrating is a function, right? So if I see something like, if these are my two curves, I'm going, oh, this is gross. So if I have to integrate this in the x direction, I'm going to have to cut this in half. And then I'm going to say, okay, I'm going to like think of this as being one curve, and then this as being another curve, and then this is a curve, and then this is a curve. You know what I mean? Like I have to really break it into a bunch of pieces. And you can kind of see that there's going to be this issue here because, you know, one of your things is not a function along the x-axis, right? If you integrate it on the x-axis, this yellow curve isn't a function. It sort of curls back on itself. But now if I turn my head to the side, right, I can't just turn my surface to the side because things will rotate. So you actually have to physically turn your head to the side. But if you physically turn your head to the side, well, from the y-axis, Now there's only one curve, right? I don't need to break this up anymore. This is the upstairs curve, and this is the downstairs curve. And so this is probably going to be easier to integrate along that way, right? So yeah, that'll probably end the 24-hour test. Things will be on purpose again. Yeah. So can you be specific too about like what about this curve you wanted me to repeat? Do we have to mention using Desmos? No, I mean, like, so this is a great question. Do we have to say I used Desmos? Desmos can never be used to justify anything. So you can't say by Desmos, I know that this function has a root at 7 or something like that. But what you can do is you can use this yourself in order to figure out what the root should be and then show that it is a root. Do you know what I mean? Like if I gave you a function f of x is like x squared minus 5x plus 6, like you might forget how to factor. You plug this into Desmos and you're like, oh, 2 is a root of this. Of course it is. Maybe I should try and factor out an x minus 2, something like that. So you won't be able to use Desmos to justify, which means you generally don't have to tell me. If you do want to tell me, great. I mean, you're not going to lose marks for that. But it can't be your only justification for why something is true, right? Like you can't plot it and say by Desmos, this has a min here. You have to still show that that is actually a min mathematically, right? For this question, the integral will be the green function minus the yellow function if we integrate along the y-axis. Exactly. Yeah, exactly. And that's why this is going to be easier to integrate along the y-axis, because it's just green minus yellow, versus if you do the x-axis, you've got yellow minus yellow plus yellow minus green, and it's, that's weird. That's kind of awkward. The thing's graphable. Yeah, absolutely. I mean, for me to make a function that isn't graphable, I'd have to use things that you guys probably haven't seen before, right? Yeah, Tidor, exactly. You do whatever is easier. Now, in theory, I could ask you to do both, right? Like I could totally give you this. And I think actually this is something I have done in a final exam before, where I give you this intersection and I say, write it as a y-axis integration, write it as an x-axis integration, and then solve one of them, like whichever one you want, right? And that is exactly an exam question that I have given in the past. So you definitely want to be comfortable using both of those. So I strongly recommend that. Use octave before and lost marks. Jacob, you should do a remark for that, because we're very clear that like octave can be used. And in our solutions, I often say like by octave, we can do this, right? For this, like when the curve is negative, do we have to separate the interval? No. So the great thing is about this is a great point. I'm really sort of glad you brought this up. So let's say, let me draw something a little bit different. So let's say maybe here we've got a blue curve, and then here we've got like a green curve like this, right? So because you're doing the area between the curves, right, you don't have to worry about the fact that this function goes beneath the x-axis. Okay, when you subtract the green from the blue, it will account for the fact that the blue function is already beneath the x-axis. Okay, so you don't need to worry about that. It will account for this automatically. Does that make sense, Kelly? Like, do you see that that's true? And to maybe help you to like convince you of that, let's do a really easy example. So a really easy example we could do is, what if one function is like y equals 2, right? And then the other function is like y equals -1. And we would say something like, oh, okay, well, the y equals -1 function, that function is beneath the x-axis. So that area should be negative. And yeah, it is. But what are we going to do? We're going to subtract, right? When we do the integral, we're going to do 2 minus -1. So even though we're going to get a negative area here, it's going to get subtracted to give me, right? What's that distance? That distance is 3. That area, that negative area gets subtracted, and so it ends up becoming positive like that. Yeah. Yeah, Jacob, good. I'm glad that you did. Yeah, it's true. Sometimes TAs, so for the record, TAs in this class are really hard to find, right? Because most of you don't go on to be math majors, but some of you actually need to do some math stuff before you can TA this class. So it ends up being quite hard to find TAs for this class. Okay, so does that help everyone? Does everyone see it? Now I was asked to talk about like monotonicity and subnormality. So a person who asked me that, I remember who you are, but I don't want to necessarily dox you. Can you talk about like what specifically? So monotonicity of the integral says if f of x is less than or equal to g of x on the interval a, b, then the integral also satisfies this identity, right? And I mean, we haven't done too many things where they're applied. I guess actually, no, that's not true. Like we literally just did this. So here, for example, we used monotonicity, right? In this problem, notice I could have written a of x as, right? So a of x is right here. So I could have written this as a of x is the integral from 0 to x f of t dt minus the integral from 0 to x g of t dt, right? And we said, okay, well, let's look at an interval, right? So if I look at 0 to a half, so if I look at this interval right here, so on 0 to a half, right, we have what, g of x is greater than or equal to f of x, right? So what does that mean? That means that the integral of g of x from 0 to a half is greater than or equal to the integral of f of x dx, right? So that means that a of x, which is the difference between these two things, is less than 0. Does that make sense? Like we actually used that when we did this problem. We kind of like, we weren't too worried about it. Like we kind of just, used it implicitly, but we're using the fact that if one function is bigger than the other, then it has more area under it, right? And again, hopefully that's sort of like intuitively obvious. And again, all I want you to sort of have here is the intuition, is that if one function is bigger, so if this is f, and the other function is smaller, then when I compute the areas under these functions, well, which function is going to have more area? Probably the blue one, right? Because it's bigger. And that's all monotonicity says, is the bigger function has more area under it, and the smaller function has less area under it. And again, we use that in this problem sort of implicitly, but just keep in mind that sort of intuition that that's true. Subnormality, you typically don't have to worry about. It's not something that will come up a lot in this class, but subnormality is this statement. So okay, and let me show you an example of where this would be true. So the integral on the left, let's say my function looks like this. Okay, and this is A and this is B. So the integral on the left says find the area. And we know that integrals are signed area, right? So the stuff above the x-axis is positive and beneath the x-axis is going to be negative. So when I compute my left-hand side, I get all that cancellation happening, right? And so the area is actually going to end up being relatively small. So, right, there's cancellation here that can happen. And then just the absolute values at the end, just make sure your answer is positive, right? But generally you compute the integral, you get a bunch of cancellation. Now over here, when I take the absolute value, what I've done, let me see if I can draw this. I'll try and draw this in black because I think it's the only color I haven't used. So the absolute value function looks like this. Yeah, that's too big. Right? It's kind of like everything that's above the x-axis stays above the x-axis. And then anything that's beneath the x-axis gets put above the x-axis. So now there's no cancellation, right? All that area ends up becoming positive now. So all this thing says, this subnormality, is that if you take the function and put it so that all of it is above the x-axis, that area is bigger than if you let some of it be beneath the x-axis. Does that make sense? Like that's the intuition behind what subnormality is telling you. If you take it, put it above the x-axis and compute the area so that all the area is positive, then that's going to be bigger than if you allow some area to be negative. That's what subnormality says. Okay? And again, we're typically not going to use that. Like that's not going to happen a lot. And any sort of situation we could come up with is going to be similar to where you can just use this intuition. Inherited, what's the inherited, like the inherited integrability? I just need to double check what I said about that so I know. So it just says if you can find the area on a subinterval, then like, yeah, I wouldn't worry about that. That's just sort of like things make sense, but let me just pull it up so I know exactly what I said here. Do you remember where it was? It's in properties of the integral, right? Yeah, okay, so it just says, so we never talk about functions that aren't integrable, but there are functions where you can't find the area, right? But it just says, hey, listen, if you've got a function and you can find the area under it, then if you restrict it, right? So like now, let's say I restrict it from here to here. So if I can find the area on the big interval, then I can definitely find the area on the small interval, right? And sort of intuitively, you're like, yeah, that's true. Now, this one you really don't have to worry about because when we only ever work with integrable functions, right? I've never given you a function that isn't integrable. So you don't have to worry about that because we don't necessarily play with those sorts of things. But again, it's just sort of like a sanity check that should be stated in there so that you know that in theory you can do this. Okay. So, and those were the only three that were bugging you? Hopefully, week 8, 11. Okay, cool. So I got asked for the winter week 8 poll questions. Problem 11, question 11. Ooh, okay, sure, yeah. So this is the week 8. Oh, let's not use blue. So this is the week 8 polls, question 11. And here we're asked to do the integral of x to the power 5 e to the x squared dx. Okay, and this is a really nice one. So I do something I think similar to this in the notes where I do x cubed instead of x to the power of 5. Now in the notes, I go straight to a substitution and I do it in a single substitution. I generally don't advise that though. Okay, we kind of want to break this into 2 parts. I want to do a substitution and then I want to do an integration by parts. So here's how I think about this problem, because it's not enough if I just do it. You're gonna be like, how would I know how to do that? When I look at a problem like this, what I'm trying to do, yeah, Kelly, I don't know, but let's work it out and then we'll know. When I look at a problem like this, I say, what about this do I hate the most? Do you know what I mean? I look at a substitution or I look at an integral, I say, what do I hate the most? Now this x to the 5 here, it's not bugging anyone, right? It's living its best life. Let's leave that alone. Let's not worry about that. The thing that's pissing me off, exactly, it's that e to the x squared, right? I don't like that x squared up there, right? So that thing is pissing me off. So I'm going to substitute that away. That's sort of the idea. And even if you don't know if it's going to work out, just give it a shot, right? Like what's the worst that can happen? So let's let u be equal to x squared. Du is 2x dx. Okay. So again, I'm going to commit blasphemy and I'm going to mix my x's and u's, okay? Just for the sake of teaching you all what's going on. So I've got x to the power of 5, e to the x squared. Well, I guess that's going to become e to the u. And I've still got my dx here. Now, it's up to you, again, whether you solve this for dx or not. The way I sort of think about it is I would say, okay, I'm going to keep 4 x's. And then I'm going to use 1 for my substitution. Do you know what I mean? Like I need 1 for the substitution, right? Because I have an x here. So I need 1. So I'm just going to pull it to the side and put it with the dx so I can substitute it. Now, some of you might solve for the dx instead, and that's totally okay. That has the exact same effect. So if you want to solve for dx, and want to write this as dx is du over 2x, and then plug that in, that's totally okay. You can do that. Okay, so I'm going to do this. I'm going to get x to the 4. Here, let me pull the 1/2 out. X to the 4 e to the u du like that, right? I suppose, Saeem, like you're right. And somehow the worst that could happen is that you fall into a chronic depression and throw yourself in front of a bus. But like, we're trying not to go down those like really dark lanes, right? It's sort of like, what's the worst that could happen? Realistically, you waste a little bit of time and you find out your substitution doesn't work. But the alternative is you don't try it and you don't get anywhere either, right? Which results in the same sort of thing happening. So I guess sort of like, it's not what's the worst that could happen. It's that you won't be in a worse position than if you didn't do anything, right? Like if you didn't do anything, then you're still not in a better position. So you might as well try it, right? That sort of thing, right? Okay, yeah, sure. So, yeah, so try it, right? Just find out, and what's the worst that can happen? And I find, again, without me ranting too long about this, some students are really afraid to write down something that's wrong, and I can't discourage you from doing that enough. Writing down stuff that's wrong is really important. Try not to do it too much on a test, right? For obvious reasons. But when you're learning and there's no stakes, right? I'm not being marked on this. If there's no stakes involved, write down wrong stuff. That's the best way to learn, right? The best way to learn is legitimately to make mistakes. And if you're too afraid of making mistakes that you won't even write stuff down, that you won't even try, you're not going to learn, right? So make mistakes when it doesn't cost you anything. And that way, when you get to the test and it does mean something, you've done all your learning already. So write it down and see what happens. Okay, so I get to this point here, right? And I'm like, okay, I still got some x's left over. I couldn't get rid of those. And now you go back to your substitution and you say, well, there's 4 x's there, x to the power 4. U is equal to x squared. Okay, yeah, that's pretty, I can get rid of those, right? That's u squared. So I'm going to go in here and I'm going to u squared that away. Boom. All right, got rid of all my x's. I'm in a good place. So I stare at this now and I say, well, is this better? Yes, I think it is. It's not perfect, right? It still needs a little bit of work, but we're definitely in a better situation here. What do I do now? Probably integration by parts. Exactly, right? I think a couple people, you see that, right? When you got that like u and you got that e to the u, even if it's u squared, who cares? Let's do some integration by parts. Okay, now actually I really regret using u as my variable. So everyone, let me just change it to a y because I want to use u for my integration by parts. So I don't want u's to be everywhere. So if you'll just let me go through and change these all to y's, hopefully you won't yell too badly. Right? It even kind of looks like a y. Okay, so there's 2 things I got to hit there. Where did the half come from, and how does x to the 4 become u squared? Okay, so that half is this 2 right here, right? So I've only got x dx, so that means that it becomes dy divided by 2, right? So maybe let me put the dy. It becomes dy divided by 2 like that, and then I pull the half out. Does that make sense? For that part, we're good on the 2? Okay. And then x to the 4, so we know that y is equal to x squared here, right? So that means that y squared is x squared squared is x to the 4. And because my goal is to get rid of all the x's, I don't want any x's, right? I only want y's. So I look at that x to the 4 and I say, how can I turn those into y's? Oh, y is x squared. That allows me to write this as x to the 4 as y squared. Is that one good too? Is that all right? Right? You have to go back to your, if you've ever got like x's or anything left over, you have to go back to your substitution and use that to get rid of the stuff, right? That's what you got to do. Okay, so our goal now, integration by parts. And again, I sort of look at this. I know I want to differentiate the polynomial and I want to integrate the exponential because I can integrate the exponential no problem. Can I do, yeah, wait. Let's go back and sub again so you ensure all the, yeah, exactly. Yeah. Yeah, exactly. You can just keep on substituting out as much as you want until all the x's are gone. Because if there are any x's and y's, you're in trouble. You can't do that, right? All your x's have to disappear. So you just keep going back and keep applying your substitution. You say we got to put it back to this, but how would you? So, I mean, I don't think it's a matter of remembering that. It's that when you do a substitution, you have to get rid of the original variable. Do you know what I mean? So when I'm going through this process, I got rid of as much as I could, and I got to here. And I said, well, damn, I've still got some x's. Do you know what I mean? Like, I have to get rid of all the x's when you do a substitution. You're not allowed to keep them. So if I get here and I go, well, I've still got some x's, how do I get rid of them? How do I turn them into y's? Well, I go to the only equation I have that's relating x and y, right? This is the only, like, that equation is how you turn x's into y's. So that's, you know, I just do as much as I can until I get stuck. And then when I get stuck, I say, well, that's the thing I have to use because it's the only thing I can use, right? So that's how I do it. But Arslan, that is not the antiderivative. So what I want you to do is differentiate that thing. So differentiate that thing on the right and see if you get the thing on the left, right? Because you can always check an antiderivative by differentiating it and seeing if you get the answer. And if you do that, you're going to have to use the quotient rule, and you'll see it doesn't cancel out. It doesn't work out nicely. I mean, you tell me, is it close? The answer is more, so first of all, close doesn't matter, right? Close isn't good enough because there are lots of things that are close, but, you know. So the integral of x over 1 plus x squared dx is 1/2 ln 1 plus x squared. Okay, the integral of 1 over 1 plus x squared is arctan x. The only difference between these two things is this x right here, right? The x in the numerator. And yet they gave you completely different answers. One of them gave you a logarithm and the other one gave you an inverse trigonometric function, right? So close isn't good enough. You really have to hit it on the head. And if you do that one, you'll see it doesn't work. And in fact, there is no elementary antiderivative of e to the x squared. Okay, you can't write this thing down in terms of any functions that you know. So that's why when I see that e to the x squared, I say, nope, I am not messing with this thing. I am getting rid of that x squared because it is bad. Okay, it's doing some bad stuff for me. Where did the 5 go? Here's the fifth derivative right here, or here's the fifth x, right? So you see there's 5 x's total, but I needed 1 x in order to do my substitution. So Ahmed, do you see that? So I had to take 1 x out so that I could do my substitution, and that's what left the other 4. Okay, so in terms now of substitute or like integration by parts, we're gonna let u be y squared. So du is 2y dy. We're gonna let dv be e to the y dy. So v is e to the y. And if we plug this in, we're getting a 1/2 uv minus the integral of v du. So 2y e to the y dy. Good, we've definitely improved our integral. You sub in dy over 2. Yeah, I think, that's you helping someone, Sam, I hope, maybe? Okay, cool. Yeah, because I've got a bunch of direct messages too, which kind of like dilute who you're maybe answering to, and then I have to check, is it a direct message or not? Okay, and so we're gonna have to do integration by parts again here. So we're gonna let u be y, because I'm just gonna take the 2 out. So du is dy, dv is e to the y dy, v is e to the y. All right, so if I do this now, what do I get? So I get 1/2 y squared e to the y minus 2 times y e to the y minus uv minus v du, right? So you can see I'm still even using the mnemonic there. All right, so what do we get? So we're gonna get 1/2 y squared e to the y minus, that 1/2 cancels that 2, which is nice. So I'm gonna get minus y e to the y. Now, don't forget double minus sign. Be careful about this. That burns students a lot. So plus e to the y like that. And then my answer needs to be in terms of x. So I plug y equals x squared back in. I get 1/2 x to the 4 e x squared minus x squared e to the x squared plus e to the x squared plus c. And if you really want, you could do some factoring. You could pull out like an e to the x squared. You get like x to the 4/2 minus x squared plus 1 plus c, like that. Kelly, is that what you got? Sweet, there you go. All right, so sometimes everyone, you gotta use multiple integration techniques. I mean, that's life. What are you gonna do? And again, we only know 2. If you went and took 136, you'd have a lot more than 2, let me tell you. All right, next one was week 9, question 4. Yeah, might start accelerating just because there are a bunch of people who wanted me to do questions. Absolute oh, beautiful. Okay. So this is week 9, poll question 4. So it says find the absolute area under the graph of this thing. Okay. And it gives an interval on -2 to 2. So immediately I can see this function is odd. So, and again, you're free to use Desmos. You can plug it in if you want. You see the function is odd, but either way, what you're going to have to do is you're going to have to integrate its absolute value. So I know that the integral from -2 to 2 of the absolute value of this thing is going to be, absolute value should be on this side. That's going to be just double this one, x squared plus 1 dx. Does that make sense? Does everyone see what I've done there? Week 7. I don't know if I'm going to get there same, but I'll try. Okay, so now we just need to integrate this. Yeah, exactly, because it's even, or because the absolute value is even. And so if you want, plot the absolute value of x divided by the square root of x squared plus 1. Plug it into Desmos, see what you get, and you'll see, yeah, it works out. We need to now do a substitution. So I'm probably going to let u be x squared plus 1. Du is, hey, look, 2x. I'm going to put that 2 inside. So we actually get 2x dx. Isn't that exciting? That never happens. U of 2 is equal to 5. U of 0 is equal to 1. So I'm going to get the integral from, what did I say, 1 to 5? 1 to 5, 1 over root u du. All right, FTC. So this is -1/2. So this is going to be 2 root u from 1 to 5. So this is going to be 2 root 5. Let's put the 2 out here. 2 root 5 minus 1, like that. How do I add a 2? Oh, no, so, right, yeah. So this 2 is actually out here, right? It's because the integral is, the function is even. So you only have to do its integral to the right of the x-axis, and then you can just double it. Do you know what I mean? I don't know exactly what this function looks like, but it looks, something like this. Well, when I take the absolute value, that's not what it looks like. So when you take the absolute value, the function looks something like this. So it's the same on both the left and right, and you're trying to find its area, so just find the right-hand side and double it. So Kelly, strictly speaking, every time you do a substitution, you have to change the bounds, unless it's an indefinite integral, right? If there are no bounds here, then obviously you don't have to change any bounds because there aren't any bounds to change. But anytime otherwise, if there is a substitution, you have to change the bounds, okay? You don't have to change the bounds for integration by parts, but for substitution, where there are actually bounds of integration, you have to change the bounds, period. And that's the rule. Okay, does that make sense? And then if you want to, you can convert back, right? So instead of solving this, once I get to here, if I want, I can turn this back into x's. And if I do that, then I have to change the bounds back as well. And that way you get the same answer, right? So you have to change the bounds, but if you want to, you can revert the bounds by reverting back to X instead. So that is an option that you can do, but if that confuses you, don't worry about it. Just remember, always change the bounds. Okay, 9-4 and 9. Oh no, I was also asked for question 5 here. But I want to kind of split it up. I feel I did question 5. Question 5 was a poll question. So whoever asked me for that, go check out last week's poll questions, because I am pretty sure I did question 5. Can someone confirm for me that I did do 5? I'm pretty sure I did. That's that one that looks like this. Right? And we had to find this area. And you guys remember that? Yeah, I think I seem to recall doing that. So go and see if you can find that. Okay, so 9-4, 9-5. I did 9-4 as well. So 9-4 is you've got y is equal to x squared, right? And then y is equal to 4. And then you want to find the area, or you want to find the curve that splits that into 2. I definitely did that in office hours as well. Let me try and find it real quick. Hopefully I can find it. So when was this? So this was last week, which would have been, where is it? Where are you? Is this even the right? Does anyone know where it is? Did I do this Tuesday or Thursday? Does anyone remember? Oh, okay. Ooh, I got one of them. All right, here is, so here's 9-4. And then maybe Thursday I did that one. Yeah, and it's like the first thing I did on the Thursday lecture by the looks of it. Is it the first thing I did? Yes. So for question 5 of poll week 9, that's just what I did last Thursday. So you can check those out. Now 9-5. Oh man, running out of time. Let me see if I can just set it up. Try and get you to a point where you can solve it. So 9-5 is, you've got the curves y equals mx and y equals x cubed, or find the value of m such that the area bounded by these two curves is exactly 8. Okay. So y equals x cubed is like this. I must want m to only be, oh no, I guess not. Okay, sure. No, this will always cancel each other out. So I must only want the positive x-axis. So if that was confusing you, maybe that's part of the issue. So let's only do the positive axis. So we've got y equals mx, we've got y equals x cubed. Where do they intersect? So we get mx is equal to x cubed. So we get x times x squared minus m is equal to 0. So that's x equals 0 plus or minus root m. Obviously, we throw away the negative solution. So this is square root m here. And then the integral is mx minus x cubed from 0 to root m. You want that to be equal to 8. And now solve for m. Right, because you can actually compute this. It'll depend on m though, but you'll get some sort of equation. You can set it in m, you can set it equal to 8, and then you can solve it. Okay, so that's 9-5. And then the last one, so I've been asked to do the week 7 stuff. I don't know. I don't think so, you particular, unless you were one of the ones who asked this question. Did you ask for 9-4 or 9-5? Okay, so 9-4 is up there, is one of those YouTube links, and 9-5 is this problem right here. I'll try and post the video tonight, and you'll be able to check it out. Week 7, question 10 and 11. Okay, so the week 7 question 10, this is a really good one. And I think I actually started to answer this on Piazza. So we have g prime of x equals 1 over x f prime of x minus 1 over x squared f of x. F of 1 is 1. G of 1 is 0. And then the question is, what is g of 2? So the trick here is to say, okay, this looks like a product rule, right? So let's create, let's say the g of x is some function, is h of x times f of x, but we don't know what h of x is, right? So if we differentiate this, we get g prime of x is h of x f prime of x plus h prime of x f of x. And if we compare that to this, and we say, is there an h of x which does this? The answer is yes. H of x must be 1 over x, right? So that tells us g of x is f of x over x. So g of 2 is f of 2 over 2. And how could we possibly do this without knowing what f of 2 is? Oh, right. Sorry, plus a constant, obviously. Tyler's being dumb. Plus c. In order to figure out what that constant is, you plug g of 1 in. You know that's 0. That's going to be f of 1 over 1 plus c. So that tells you f of 1 is equal to 0. So you get g of x is f of x over x plus minus, what did I say f of 1 is? F of 1 is 1. So c is equal to negative f of 1, which is negative 1. So this is going to be minus 1. And then g of 2 is f of 2 divided by 2 minus 1. Right? So really the crux of this is realizing that this is true. No problem, tutor. I'll see you later. Good luck on your test. Okay, and then week 7, question 11, which I guess is the last one, is the same sort of thing. So this is now week 7, question 11. So we've got g prime of x is x f prime x squared. We're told f of 0 is negative 1, f of 1 is 2, g of 0 is 0. Okay, and then it says what is g of negative 1. So again, we look at this, and this one actually we can probably do now. See you, Davin. See you, Kelly. This one, see you, Arslan. This one we can probably, you can actually do with substitution, right? Like let u be equal to x squared. And if you do that, you'll just get g of x is 1/2 f of x squared. So you can actually do that one with substitution if you want, plus some sort of constant. We need to figure out what the constant is. So g of 0 is equal to 0. That's 1/2 f of 0 plus c. So it's going to be 1/2 negative 1 plus c. So that tells us c is equal to 1/2. So now we get g of x is 1/2 f of x squared plus 1/2. So it says, what is g of negative 1? So g of negative 1 is 1/2 f of 1 plus 1/2. F of 1 is 2, so we get 1/2 times 2 plus 1/2. So that should be 3/2. And that is answer B. Okay, so yeah, I mean, I definitely went through that a little bit quick. But any questions? Yeah, no problem. Okay, everyone. I'm going to call it. I got a couple things I got to do, and then I got to release your test tonight. So there's some work to be done. But good luck, everybody. Work hard. Hopefully it makes sense. Don't hesitate to ask questions on Piazza. And otherwise, have a good weekend. I'll see you guys next week. All right. Bye, everyone.